going to start looking at logarithmic functions. Now you may ask, what is a logarithm? Well, a logarithm is just the inverse of an exponent. I really enjoy logarithms because I feel like it's one of the last barriers in mathematics that we really encounter is how to answer one of those last questions that may come up. And it deals with how to answer questions about exponential functions. And if you'll always keep in mind that math symbols don't do anything. Math asks a question, and it's up to us to answer. We either answer the question, it's there, or we don't answer the question, and we use math symbols to keep that question front and center until we are able to answer it. So just think about what an exponent asks. Exponent asks, what's the product if I multiply the same number by itself a specific number of times? So for example, if I had 3 squared, what's the product if I multiply this number by itself this many times? Well, we all know that. That's 9. 3 squared equals 9. Easy enough. Logarithm asks the inverse of that. Logarithm asks a different question. It says, how many times was a number multiplied by itself to produce a specific product? So logarithm says, and it'll be written like this, log base 3 of 9. How many times was this number multiplied by itself to produce that number? Well, what's the answer? We all know that. 3 was multiplied by itself 2 times to produce 9. That's the idea behind logarithms. They ask a different question, or they ask take an expression or a relationship that we've worked with for many years and look at it from a different perspective, from the inverse perspective. So it's what exponent produced this product instead of what was the product. So if you can always keep that in mind of what a logarithm is asking, logarithms are a very easy, very trivial thing. They don't seem to do a lot, but they actually open up. They seem trivial, they're not trivial. But they open up a lot of doors and kind of knock down a lot of barriers. A lot like the imaginary unit did for us, in that it said, oh, we now have all these non-real answers that we can go and explore and just say, I don't know how to do that, and then we're stuck with it. Logarithms kind of do the same thing. We may not know the answer to a specific one. What exponent causes 5, or how many times do I multiply 5 by itself to get 10? I may not know the answer to that, but I can make notation of that and use that information, and maybe later on it becomes something that is answerable. So think of it kind of like we did with the square roots when you first started exploring square roots. Square root says, what number multiplied by itself produces this value? Okay, well, if I have 16, that's easy. Square root of 16 was 4 times itself. If I had 9, that was easy. That was 3 times itself. Well, if I had 12, I don't know that. I don't know what the square root of 12 is. I don't know what number times itself equals 12. I know it's not a rational number. I know that there is no rational number times itself that's going to equal 12. So what would we do? Well, we simplified that, right? We would make 12 into 4 times 3, and we'd say, okay, I know the square root of part of that, of one of the factors. So we could simplify it into 2 square root of 3. But we were still stuck with that portion we didn't know how to answer. What's the square root of 3? What number times itself equals 3? Well, that's what logarithms are going to do. Sometimes we can answer the question, log base 3 of 9. What number times itself, or sorry, how many times do I multiply 3 by itself to get 9? The answer is 2. If I said log base 2 of 16, how many times do I multiply 2 by itself to get 16? Well, the answer is 4. We know how to answer that. But if I said log base 5 of 10, how many times do I multiply 5 by itself to get 10? I don't know the answer to that question. So there is no rational answer to that. So what do? We make note of it, simplify if we can, and we're going to explore some ways to simplify those and pull out the pieces that we can. But a lot of times it's like with radicals. That question is just going to tag along until we can actually do something. And many times you just have to go grab the calculator and let it do the calculations. just like you did with the square root. If I need to know that answer so I can actually use that answer, what's the square root of 3? I'm going to go over to the calculator and it's going to tell me 1.866 roughly. And then I'm going to go use that 1.866 wherever I need to. Well, if I need to know what log base 5 of 10 is, then I'm going to go over to the calculator, type in my log base 5 of 10, and I'm going to get that decimal approximation. I'm going to use that. But that's what logarithms do. They just ask a different mathematical question. So if you can kind of keep in mind what a logarithm's asking, they're not very hard, they're not very complex, but they do open up a lot of doors, a lot of possibilities. So give me a few minutes, I'll get some stuff up here and we'll get to explore the relationship between exponents and logs and all that good stuff. Okay guys, here I've got a few examples that we're going to look at, just working on moving comfortably from exponent form into log form. Right now these are all true statements, we're not doing any math here, we're just, like I said, being able to move from one form into the other. So that when we get to questions that are not obvious or things we don't know, or say we have an equation that we're trying to solve or maybe something we're trying to graph, we can move it from a form we're not comfortable with into a form we are comfortable with and then go from there. So right now if we want to write in log form, think about what log form is. We said it before. Log asks the question, how many times did I multiply this number by itself to get this number? So that's what we're going to write. Log base this number. So this number times itself, how many times to get this number? And the answer is 3. So what I'll tell people typically is start with your base and just work your way around the equal sign. Log base 5 of 125 equals 3. Log base 5 of 125 equals 3. So start with your base, and we still call this the base. Okay, so it doesn't matter if it's this form or this form. This is the base of the log. This doesn't really have a name. I'll call it the log value. I don't know why it doesn't have a name. I haven't been able to find a name. We name everything in math. We even have a name for the numbers after a decimal point, but for some reason I've not been able to find a name. I've never ever heard a professor or anyone give it a specific name. I just call it the log value. So this number here, it's a subscript, so log subscript 5 of 125 equals 3. So that's the base, that's the log value, and that obviously is what it equals. So if we're looking at this one over here, we're going to write it in log form. Again, start with your base and work around the equal sign. So log base, what? What's our base? Well, our base is 1/3. What are we taking the log of? We're taking the log of 9, and it should come back and equal that exponent, right? 1/3 raised to what power equals negative or equals positive 9? Well, we know that that's got to be negative 2. So logs can equal negative numbers. As we see right here, we have a log equal to a negative number. In a second, we'll look inside, can we take the log of a negative number? And that's going to get into us looking at the graph. But so that's moving from exponent form into log form. Start with your base, work your way around the equal sign. So log base 5 of 125 equals 3. Log base 1/3 of 9 equals negative 2. We're going to use that same idea when we're going from log form into exponent form. And remember what exponent form says. It says this number this many times equals this value. So 2, how many times equals 8. So that's just moving from log form into exponent form. It's the same thing. Start with your base, work around the equal sign. 2 to the 3rd power equals 8. So if we looked at this example, start with our base, work around the equal sign. 4 to the negative 1 equals 1/4. 4 to the negative 1 equals 1/4. So again, that's moving from one form to the other. We haven't done any math. We're just changing up the way it's written. And just think of it kind of like I can write 2 plus 2 plus 2, or I can write 2 times 3. Multiplication form, addition form and multiplication form. It's two ways to write the exact same expression. Both of them equal 6. So I'm just changing up the way we're writing it so we can move from one form to the other later on. Give me 1 second and I'll get some information up here and we'll talk about what the graph of a logarithmic function actually looks like. So let's look at what's going on with logarithmic functions graphically. As I mentioned before, a logarithm is just the inverse of an exponent. So let's kind of quick review, go back to our exponential functions. So in our exponential functions, remember, we use these same 5 points there. Just plugged in 2 to the negative 2 was 1/4. 2 to the negative 1 was 1/2. 2 to the 0 was 1. 2 to the 1 is 2. 2 to the 2 is 4. So we just substitute our x's in one at a time. We get these points. So negative 2 was at 1/4. Negative 1 was 1/2. 0 was a 1. 1 was a 2. And 2 was a 4. So we had that curve right there. And if you'll remember, we had that horizontal asymptote. Oh, okay. Horizontal asymptote sitting there at y equals 0. So if you'll remember, domain was negative infinity to positive infinity. And range was 0 to positive infinity. Well, let's look at what's going on with logarithms. If the logarithm is the inverse, 2 to the x, the inverse would be log base 2 of x. So, I picked some points here that are easy to work with, things that we should know what the log is. Remember, log asks the question, what exponent causes this to happen? So, 2 raised to what power is 1/4? Well, it's reciprocal 2 times, so negative 2. 2 raised to what power gives us 1/2? That's just reciprocal 1 time, so that's negative 1. 2 raised to what power gives us 0? Sorry. 2 raised to what power gives us 1, which is 0. 2 to the first power gives us 2. 2 to the second power gives us 4. So if we go and then plot those points, at 1/4 we're at negative 2. At 1/2 we're at negative 1. At 1 we're at 0. At 2 we're at 1. Sorry, I'm having trouble getting my point, saying my point straight. And at 4 we're at 2. We get this picture right here. So as you can see, what's going on is, instead of us getting the horizontal asymptote at 0 like we did on the exponential function, we're going to get a vertical asymptote at x equals 0, which should make sense. Okay, so we should see that our restriction, I shouldn't be able to plug in any negative numbers here. I shouldn't be able to say, I'm taking a positive number, multiplying it by itself, and it's going to produce some negative value. Okay, as we discussed before with square roots and imaginary numbers and things, that's what caused us to have the imaginaries, because we couldn't take a value and multiply it by itself and get a negative value. Well, you can't take a positive number, and that's one of our restrictions on exponentials and logarithms, is the base has to be positive. You can't take a positive number, multiply it by itself any number of times, and it produce a negative number. So 2 to no powers is ever going to be equal to a negative value. So in this case, we have this vertical asymptote. There are no negative x's that we can plug in. So we should see that our domain, in this case, is everything from 0 to positive infinity for this specific function. Remember, we could shift this whole graph left, put a horizontal shift on there. And what's the range going to be? Well, as we can see, the range, it's going to go down forever. We can keep plugging in smaller and smaller and smaller, numbers closer and closer and closer to 0, and they're going to give us lower and lower, more greater negative exponents, right? So 2 raised to a huge negative exponent would produce a very small number. So if I'm doing log of a very tiny number, that means I had a big negative exponent. It equals a large negative number. So we end up seeing that our range can go all the way from negative infinity up to positive infinity. It's going to keep growing on up there. So negative infinity to positive infinity, and that kind of just goes back to what our definition of inverse is, right? The inverse means they undo each other. So the domain of one function becomes the range of the other. Range of one function becomes the domain of the other. And we could see that here when we graphed. All we did was swap those domain and ranges. So that's graphically what's going on between an exponential function and its logarithmic inverse, or its inverse function. So again, domain and range of this really simple one, it can adjust based on if we're going to put translations, shifts and reflections and other types of transformations in there. Give me a second, I'll put a few more interesting properties about logarithms up. So guys, here we can see our official rules for logarithmic functions. If we have log base b of x, b has to be greater than 0 and b cannot be equal to 1. And it just works off the same b, the same base that we had when we were talking about exponential functions. So they've got those same rules because we look at logs as the inverse of exponential functions. A couple of terminology and notation things. A log we use a lot is log base 10. We call that the common log because we use it so often. So that's just log of x. So if you don't see a base there, it's an understood 10. Not understood 1, an understood base 10. Same thing with something we call a natural log. If we have a base e, we don't write base e. Remember, e is that natural base, the 2.71828-ish. So we don't write log base e. We abbreviate that ln. So that just stands for logarithm naturel. It's a French thing. So it's the natural log, but we write the log natural. So ln of whatever we happen to go with. So it's just, again, notation things and terminology things. So if we don't see a base, these are the only two times we won't see a base given. If it's log with no base, it's understood base 10. If it's ln, which obviously will have no base, it's going to be an understood e right there, or 2.71828. Now let's quickly go through and try to evaluate a few logs, just some quick ones that we should be able to work through. So remember, what does log ask? What exponent, or how many times do I multiply 2 by itself to get 32? So as I'm working through that, I know 2 to the first is 2, to the second is 4, to the third is 8, to the fourth is 16, to the fifth is 32. So log base 2 of 32 is 5. 2 to the fifth equals 32. Let's check the second one here, or work the second one. Log base 3 of 81. So how many times do I multiply 3 by itself to get 81? Well, we should know 3 to the 4th power is 81. So it's just really going through and asking your exponent questions in a different order. Here, log of 1,000. Well, we don't see a base, so we know it's the common log. It's the understood 10. If you need to, write that base 10 in there, that's fine. And then 10 to what power is 1,000? 10 to the 3rd power is 1,000. And finally down here, log, again, we don't see a base, so it's that understood 10 of 100. So we know that if I've got a whole number base, and then we end up with a fractional base, we did reciprocal at some time. So that should be equal to a negative number, because negative means reciprocal. So the reciprocal of 100 is 1 over 100. Sorry. The reciprocal of 1 over 100 is a 100. So the 100 is 10 2 times. So 10 to the second is 100. 10 to the negative second to the negative 2 is 1 over 100. So there's just a few quick evaluates. Okay guys, real quick, 2 more I want to look at. And these are ones that aren't so neat and clean to be able to evaluate. Something like log base 8 of 16 or log base 27 of 3. 8 does not have, 8 to the 0 power, obviously. is 1, 8 to the first power is 8, 8 to the second power is 64. So 8 does not have a whole number value or an integer exponent that will turn it into 16. So we need kind of a little bit different technique to be able to work through these. So what I like to do in this case, or like we have there in number 6, is I like to turn it back into exponent form and start messing around with my bases. Because I know 8 and 16 are both powers of 2, or 27 and 3 are both powers of 3, so I can use that idea that they're both powers of the same number to be able to figure out what the power of 8 is that makes 16. And here's how I like to do that. If I was to say it's equal to something, because I don't know what it is, right? So if I'm going through this and I want to think of it back in exponent form, go back through and, like we did at the very beginning, 8 to the x equals 16, right? That's what exponent or logarithm means, right? It's this multiplied this many times equals that. So if I now look at them as bases of 2, 16 is 2 to the 4th power, 8 is 2 to the 3rd power. Now it should start to work out real nice, and you should be able to see what's going on. 2 to the 3rd to the x is 2 to the 3x equals 2 to the 4th. If the bases are the same and they're equivalent, then that tells us what about the exponents? They must also be equivalent. So we can say 3x is equal to 4. So divide by 3, x has got to equal 4/3. And if you want to check that on a calculator, 8 to the 4/3 power will equal 16. So if we use that same idea for this example over here, log base 27 of 3, let's set it equal to x, because we don't know what log base 27 of 3 is. And then we work through it. 27 to the x equals 3. They're both powers of 3. So 3 is just 3 to the first. 27 is 3 cubed. Now we work through 3 to the 3x equals 3 to the first. If the bases are equivalent, then the exponents we know must also be equivalent. So 3x equals 1. So x has to equal, divide by 3, x has to equal 1/3. So this is how we can still get rational answers that are not integers. And it actually kind of sets up what a rational or a fraction exponent represents, but that's another lecture for another day. So this is just kind of another technique to be able to evaluate logarithms that still we're familiar with how these values are related, the base and the log value, but they're not directly related like the other examples that we had. That's it for now for logarithmic functions. Got a lot more with logarithms. Next lecture we'll talk about properties of logarithms, but as you can see we have up here. But logarithmic functions, and I will see you in class tomorrow, guys.